So let's talk about differential equations. So a differential equation is just any equation that involves derivatives, right? Involves differentials. So it's any equations containing the derivative of an independent and a dependent variable. So typically that's going to be a dy and a dx. So typically in AP Calculus, we're only going to deal with what we call first order differential equations. Just as an aside, most people I know, or at least I know I definitely do this, I don't actually say differential equations every single time. These are often abbreviated as diff-EQs. So if you hear people say that, if you say diff-EQs, people are going to know you're referring to a differential equation. But anyways, in AP Calculus, we're only really going to deal with what are called first order differential equations, which these only involve first derivatives. Now, we might deal with other diff-EQs that have higher order derivatives, like second derivatives and third derivatives, but typically with those, we're only going to be asked to verify solutions versus solving them. So we're going to do a verification example now. So we want to verify that this equation, y equals 2/5 times the quantity of e to the 4x plus e to the x, is a solution curve to this differential equation, right? So this is an example of a differential equation. Y double prime plus 4y prime equals 2 times e to the x. So all you're really asked to do is take some derivatives, plug them in, and make sure this works out. So the first thing we need to find is y prime. So if we take our first derivative, right, our constant's going to stay on the outside, and then we're just going to take the derivative of the inside. So the derivative of e to the 4x is e to the negative 4x times the derivative of the exponent, so negative 4. And then the derivative of e to the x is e to the x. So that's going to equal 2/5 times negative 4 e to the 4x plus e to the x. And then we also need to know what the second derivative is. So if I take the derivative of this now, got negative 4 e to the negative 4x times another negative 4 for our chain rule, right? And the derivative of e to the x is just e to the x. So that's going to give us positive 16 e to the negative 4x plus e to the x. So now when we go to verify, here we have y double prime plus 4y prime is supposed to equal 2 times e to the x. So y double prime is 2/5 times 16 e to the negative 4x plus e to the x. And then we got 4 times y prime, so it's going to be 4 times 2/5 times negative 4 e to the negative 4x plus e to the x. And that's supposed to all equal 2 e to the x. So what I'm going to do is I'm going to multiply both sides by 5/2. Because if I distribute that, it's going to cancel out those fractions. So I'm going to be left with 16 e to the negative 4x plus e to the x plus 4 times negative 4 e to the negative 4x plus e to the x. My pen would work, there we go. And then 2 times 5/2 is going to give me 5 e to the x here. So I'm going to go ahead and distribute. Minus 16 e to the negative 4x plus 4 e to the x. And then we can clearly see that the e to the 4x, negative 4x's are going to cancel out because of those opposite coefficients. And then we have 1 plus 4 is in fact 5 e to the x. Right, right? So since both sides are equal, that is a solution curve. So all that means is if you were to solve that differential equation, that would be a possible solution. And so we're going to start looking at how do you actually solve these. So in AP Calculus, we're going to be looking to solve what we call separable differential equations. So these are differential equations, so diff-EQs, where all of the x's and dx's can be put onto one side of the equation, and all of the y's and dy's can be placed onto the other side. So all this means, separable differential equations, is that you can separate your two variables. So I define it in terms of x and y because those are our typical independent and dependent variables in math. But right, you could be using any letters as long as you have two variables and you can separate them. So all of your one variables on one side and the others on the other, then you can solve it. So what's really important if you're an AP Calculus student is that you have to show this rearrangement on the AP exam if you want to earn full credit. So your little tip for the AP exam is that you must show the rearrangement of the equation. In other words, you must show separating the variables to earn full credit. Oftentimes on scoring exams, if it's a separable differential equation, it might be worth like 3 or 4 points overall to solve it, but if you don't show the separation of variables, you won't earn credit, or you'll only earn 1 point of the credit. So you don't want to lose out on all of those points if you do all the work correctly just because you didn't show that you separated the variables. So we're going to do some examples with that. So we're going to start by finding general solution curves. So this means that we're going to find a family of functions that all meet the criteria of the differential equation. So in other words, we're going to have a plus c here. So we're going to have all these same functions that if you change the constant, right, you're just shifting them up and down, but they all fit the same differential equation model. So the first thing I'm going to do is I'm going to rewrite the right side of my equation, that e to the x minus y. So I'm going to use some algebra 2 kind of like exponent rules here. I'm going to rewrite this as e to the x over e to the y, right? Because if I'm dividing two things that have the same basis, I would subtract the exponent, so I'm kind of undoing that here. So then I want to separate my two equations. So I'm going to put all the y's on the left side and all the x's on the right. So the first thing I'm going to do is multiply each side by e to the y. So I'm going to get e to the y dy over dx equals e to the x, and then we'll multiply both sides by dx. So now we have e to the y dy equals e to the x dx. So that's our separation of variables. And then once we separate our variables, we're going to integrate both sides, right? So when we see that dy and that dx, that's what would typically be at the end of our integrals. So we're going to integrate both sides, because if I do it to both sides, equation stays balanced. So the integral of e to the y, right, you're integrating with respect to y here. So the integral of e to the y is e to the y, and then integral of e to the x is e to the x, and I'm going to put my plus c on this side. So technically both sides would get a constant of integration, but you would just move one from like one side to the other and you get a new constant of integration. So you could label them with subscripts if you wanted to. I just put it on the right side. So to finish this, we want to solve for y. So we want a general solution curve. So if possible, we want to get a y equals equation. So that way we could, in theory, graph some solution curves. So I have y in the exponent, which means I need to take the natural log of both sides. So we're going to take the natural log of this side and then the natural log of this side. So that's going to give me the natural log and the e is going to cancel out. And now because of the e to the x and the plus c being inside the argument of the natural log on the right, we can't actually split them up. So our general solution curve is going to fit this right here, and that's going to actually be our final answer. So let's do one more. So over here, the first thing I'm going to do is I'm going to add my x to the other side. So I'm going to get that dy dx equals xy squared plus x. So my goal is to get the y's on the left side and the x's on the right. So what I'm going to do here is I'm going to actually factor out the x on the right hand side. So now that we've kind of done one, I'm going to kind of start doing more things in one step. So I'm going to move the dx over by multiplying both sides by dx. So that's going to cancel out here. And at the same time, I'm going to divide both sides by the y squared minus 1. So my new differential equation, apparently I'm really bad at factoring. That should be a plus 1. It's like, this isn't going to work out the way I want it to. There we go. Okay. So when we separate our variables, we're going to end up with dy over y squared plus 1 equals x times dx. And apparently, I screwed up this too. There we go. That should be a dx over here, not a dy. Okay, so we've separated our variables, and now we're going to integrate both sides. So the right-hand side is really easy because you're just integrating x, so we're going to get 1/2 x squared plus c. I'm going to have to actually add another page here, I think. There we go, just a little bit more space. And then hopefully we recognize that dy over y squared plus 1 is arctan. So this is going to be the arctan of y. So again, I need to solve for y. So I need to get rid of the arctan. So I need to use the inverse operation. So the inverse of arctan is just regular tangent. So I'm going to take the tangent of both sides. So the tangent and the arctan are going to cancel out. So y is just going to be left by itself. And then y is going to equal the tangent of 1/2 x squared plus c. And I can't go any further than that, and it's equal to y, so we're all done. So there we go. Oh, didn't actually need more space. So then those are finding general curves because we have those plus c's in there, which means that we can find an infinite number of solution curves that fit that differential equation. The last portion of solving separable differential equations is sometimes you want to find a particular solution. So we're going to do one of those to kind of finish this off. So we want to find the particular solution to the differential equation y prime equals x squared times 1 plus y if we're told that y of 0 equals 2. So what this right here tells us is that if x equals 0, y is equal to 2. So we have our what we call an initial condition. We can label that. And then we're going to go ahead and get started by solving our differential equation. So the first thing I'm going to do is write y prime as dy dx equals x squared times 1 plus y. So it's already factored for us. So I'm going to do this in one step again. I'm going to multiply my dx over. And then at the same time, I'm going to divide the 1 plus y quantity to the other side. So I'm going to get dy over 1 plus y equals x squared dx. So I've shown my separation of variables, and now I'm ready to integrate. So again, on the right side, it's pretty easy, just a nice little power rule. So we get 1/3 x cubed plus c. And now if you don't like doing all your work kind of like messily inside the problem, sometimes it's nice to just go over to the side and kind of integrate off the side. So if I want to do the integral of dy over 1 plus y, I could do a u substitution on 1 plus y. So then my du would equal dy. So that's going to become the integral of du over u, which we know is the natural log of the absolute value of u plus c. So that's going to be the natural log of 1 plus y plus c. So then I'm going to go back over here to my actual problem. and fill in the natural log of the absolute value of 1 plus y. Okay, so now I need to solve for y. So since I have a natural log that's kind of trapping the y inside of it, the inverse of natural log is e. So I'm going to raise both sides to the e power. Not to the e power, so both sides are going to become the exponent to the e function. So e to the natural log is going to cancel out. So I get the absolute value of 1 plus y equals e to the 1/3 x cubed plus c. Okay, so I'm going to start kind of labeling my c values just so you can see what's happening. No pun intended there. So I'm going to label that as c1. So I'm going to use some exponents first to break apart that 1/3 x cubed plus c1. So if I'm adding exponents, that means I would have been multiplying between similar bases. So then e to the c1, right, this is just going to equal c2, right? So e to a constant is just another constant. So now I can kind of write this like this. 1 plus y equals c2 times e to the 1/3 x cubed. So now I'm going to go ahead and drop my absolute values, and I can do that because of the c. So I can drop the absolute values here and just make this 1 plus y equals technically a c3 e to the 1/3 x cubed, and I'm going to label it as a different c because the value of c2 might change to be negative or positive depending on what it works out to be with the initial condition, and that's just going to take care of the absolute value for us. So we don't really need to worry about the absolute value because we're going to use our initial condition to plug in and just kind of solve for what our c value is. So I'm going to just keep solving for y here. So I'm going to get that y is equal to some c value times e to the 1/3 x cubed minus 1. And then I'm going to take my initial condition. So I know that x is equal to 0 and y is equal to 2. So that tells me that 2 is equal to c times e to the 0 power minus 1. So 2 equals e to the 0 is 1, so c minus 1. So 3 is equal to c. So to finish this problem off, all I'm going to do is write my particular solution by plugging in my c value and then rewriting the whole equation. Now you can plug in your initial condition as well as soon as you finish integrating. So we could have actually plugged in the initial condition here to solve for c, and then sometimes that makes it easier to solve for y equals. It just kind of depends on who you are and like what your solving style is.